All right, guys, welcome back to Chapter 10 of the Digital Investigator's Handbook. So in this module, we're going to transition to two distinctly but highly critical areas of digital forensics. We're going to be talking about the dark web investigations and database forensics. We're going to be covering things like Tor architecture, hidden services, Microsoft SQL internals, and the forensic value of, transactional logs. So for the exam, understand that investigating the dark web and databases is going to often require different methodologies. Now, we did a lot of standard disk forensics here, but we need to know how to locate artifacts that are anonymized and how to navigate the proprietary file structure of relational database management systems. These are pretty popular in the industry. Now, our learning objectives are going to be split into three main categories. I'm going to turn this down a little bit. There we go. Into three main categories. First, we will understand the dark web, including Tor, onion routing, and how to locate client-side artifacts of the dark web usage. Second, we're going to dive into the database layer. Specifically, we're going to be looking at Microsoft SQL and MySQL file structures because we may need to understand how to recover deleted files. Finally, we will learn how to analyze transaction logs to reconstruct attacks like SQL injection and data exfiltration. Now, the exam itself is frequently going to test your knowledge of where evidence resides. So a key takeaway here is that even when attackers use anonymization tools, the client machine itself may actually still have evidence for their activity. And so we may have to find where that looks like. Now, before we investigate, we must define the environment. The internet is divided into three different layers. The surface web is indexed by search engines like Google, and these are anything that's entirely public. The deep web makes up about 90% of the internet. It's not indexed, and it requires authentication. These could be things like your bank portal or medical records. Finally, the dark web requires specific software like Tor or I2P to access and relies on non-standard protocols like the .onion protocol. As forensics investigators, our goal isn't just targeting criminals, but identifying if a suspect visited the dark web or hosted a hidden service. Now, don't confuse deep web with the dark web. The exam may trick you, asking you where online portals reside. That's the deep web, versus where hidden Tor marketplaces resides, which is the dark web. Okay. I always think about deep as it's just something that's not illegal, but I just can't find it. Everyone's got a junk drawer in their kitchen or something, and maybe you threw it in the junk drawer, but we don't know exactly where it is. We just know the general vicinity. Versus the dark web is, this is, the dark alley where someone's trying to sell you some stolen merchandise. Now, Tor, or the onion router, now, this is going to provide anonymity by default, okay? When a user connects to a Tor service, their traffic is wrapped in three layers of encryption. Now, the traffic passes through three nodes itself as well. And the first node is going to be the entry node. The entry node knows who you are, but not who your destination is. The middle node knows absolutely nothing about the source or destination. It just passes the ciphertext along. And then the exit node knows the final destination and the decrypted payload, but does not know who you are. So unfortunately, the exit node will see all the traffic. Now, for the exam, I do like to say memorize the roles entry, middle, and exit node. You must know exactly what node can and cannot see. For instance, the exit node can intercept unencrypted traffic leaving the network, but it can't trace that the traffic is back to you. That's one big piece about it. Now, there are going to be client-side artifacts. Now, the Tor browser is designed to run in private mode and leave no trace. However, the underlying operating system will still remember. We can prove usage through a lot of different artifacts. And so, for instance, in Windows, we can check the Windows prefetch for tor.exe or firefox.exe to prove that the software has executed itself. We can look at the Tor state file, normally found in the data Tor state underneath the user directory, about which timestamps of when was it ran, okay? And maybe we know some of the entry guards that were used as we go through this. And then finally, if we can get a RAM dump, this is the only place where we're going to find things like the decrypted history, cookies, or any of the .onion URLs that were used. Now, we need to make sure that we can capture this memory while the Tor browser is still running. So, for the exam, know that volatility is going to be a key tool for RAM analysis. The exam is going to emphasize that live memory acquisition is absolute priority when dealing with things like Tor, okay? If you're dealing with private browsing or full disk encryption, pulling the plug instantly will destroy these artifacts and maybe even get rid of the evidence for the court case itself. So how do criminals use Tor get caught? Well, Tor creates a secure tunnel, but human error breaks it. This is known as OPSEC, or operational security. And common failures are going to include correlation, browser fingerprinting, or even metadata. Now, correlation is going to be when a suspect logs into the dark web market, as it says here, and then also their personal Gmail account at the same exact time. Now, this is going to allow law enforcement to correlate traffic timestamps throughout the logs. We can use browser fingerprinting when means that we're going to have unique configurations of screen resolution, window size, and then even installed fonts. Okay, and this is going to be used to create that unique trackable ID. Lastly, we have metadata. And uploading a photo to the dark web without stripping the metadata, the EXIF data, is going to leave things like GPS coordinates and other metadata intact. Now, we need to understand that EXIF data, exchangeable image file format, all this metadata that are stored in image files. We need to understand that it can have geolocation data, camera metadata, and that we can really use this in our collection of evidence, okay? And it's heavily tested on the CHFI, okay? Now, pivoting to the second half of our module, we're going to be talking a little bit about data forensics. Now, databases are going to have the crown jewels of any organization because they store credit cards, passwords, personal identifiable information. We investigate databases for three main reasons: to recover deleted records related to fraud, to prove data theft or exfiltration, and to identify internal tampering or DBA abuse. The common targets that you'll encounter are going to be like Microsoft SQL. Now, a lot of times it's going to be more enterprise. You'll find Microsoft SQL there. Could be MySQL or MariaDB. These are the open source versions of the software. Or even Oracle for legacy in financial systems. Now, the exam, you need to know the difference between analyzing a web server, which shows how an attacker got in, versus analyzing the database of exactly what data did they steal, or what tool did they use or modify. So when dealing with Microsoft SQL Server, you must understand the dynamic duo of its file structure. So we need to know what the MDF and the LDF files are. The MDF, the master data file, is the primary container. It stores the actual tables, indexes, procedures, and it's organized into 8 kilobyte pages. The LDF, otherwise known as the log data file, is a transactional log. It sequentially records every modification made to the database. That includes insert, update, delete. All those commands are going to be put into this file. This is a guaranteed exam topic. Memorize the file extensions of Microsoft SQL Server, which could be the MDF, the NDF, or the LDF. Also memorize the fundamental unit of data storage of SQL Server is 8 kilobytes. Now, from a forensics perspective, that LDF, the log itself, is pure gold. And the reason for this is it has every transaction. It's going to let us have what we like to call point-in-time recovery. Now, this is going to act as a complete forensic timeline of the database. It's true, forensic value lies in the fact that if a hacker maliciously drops or deletes a table, the command they used to delete it alongside of the data was deleted, but it's still going to exist in the LDF until that log is explicitly truncated or even overridden. Now, understanding the concept of write-ahead logging, WAL, is something that a database writes the change to the transactional log before it applies the change to the actual data file, otherwise known as the MDF in this case. This is why the LDF is the most reliable source of truth during an investigation, even more so than the MDF itself. Now, how do we recover records? Well, we're going to recover records through a method called lazy deletion. When a user runs a delete from user command, the SQL Server does not immediately zero out or wipe the data. Instead, it just marks the page as ghosted. Now, ghosted records themselves, these are the deleted rows of data that physically maintains intact until a background process eventually comes back and overrides them. Now, page slack, on the other hand, is the hard drive disk slack. This is unused space at the end of the 8 kilobyte page and often will also contain fragments of old deleted data. Just like on a hard drive, if you ever look at the hard drive itself, when we delete a file, it doesn't actually override the data. It just marks that page or that sector as usable for the operating system. So that way it's available as free usable space for the next file write. Now, comparing database page slack and RAM slack and file slack, these are going to be some overarching forensic principles, and they're all pretty much the same thing. When data is deleted by an operating system or a database engine, the pointers of the data is removed, but the raw data is unallocated and the slack space until physically overwritten. So I said that 3 times on the slide. I hope that helps you remember that it doesn't matter if we're dealing with hard drives or RAM or any kind of thing, any type of storage device, we're going to have slack space somewhere within the system. So in Chapter 9, we looked at SQL injection and web logs. Now we're going to look internally within the database itself. Now, plain cache, schema changes, and log anomalies are all indicators of compromise. And so the first place we're going to look is going to be in plain cache. Plain cache. I keep calling it plain. Plain cache. SQL Server stores compiled query plans in memory to speed up performance. So malicious query containing union select may still be cached in RAM. We might be able to find it here. The other place we may look for is schema changes. If there's any new database objects, attackers will create new storage procedures or triggers to help establish persistence inside of the database. And then log anomalies themselves, we need to watch out for spikes in lop read rows. Okay, this activity is inside the transactional log. A sudden spike in read operations strongly indicates either a database dump or data exfiltration. So for those who've taken CISA Plus already, remember, indicators of compromise within a database can be behavioral. While a single unauthorized select statement might be hard to spot, A script that reads, I don't know, 500,000 rows in 2 seconds is a massive behavior anomaly, and this might indicate automated exfiltration tools are at work, and we may need to look deeper into it. Now, if we shift to MySQL or MariaDB, the key artifacts change slightly, okay? So the first thing that we want to look at is going to be the IBData1 file. This is the system table space. It contains the data dictionary and the crucial metadata about the database structure. Our next file is the .ibd file. Now, if the server is configured to use a file per table, the individual table data will be stored in these files. Lastly, we're going to have the binary logs, the bin logs, is what we like to call them. This is the MySQL equivalent of the MS SQL transaction log, otherwise the LDF, right? So it's going to record all the statements and the updates to modify the data. Now, you do need to know the difference of the artifacts between MS SQL, the MDF, the LDF, versus the MySQL, which is the IB data, the bin logs, and using the correct terminology for the correct database engine. And that's going to be critical for passing scenario-based exam questions. So those performance-based questions that you like to see, guess what? This is where they like to use them, is to understand, hey, which file belongs to which database? And that's where you may want to keep in mind of. All right, so you can not just open an MDF file. You're going to need some specialized database tools. So we've got a couple tools here. We've got Apex SQL Log. This is a commercial tool that lets us look at the LDF transaction log. It shows exactly who changed what, when, and it allows you to do undo malicious transactions, okay? It's the main reason why it's commercial, is it doesn't let you do undo actions on a database. Another one would be the DB browser for SQLite. Now, this is going to be used mostly in mobile and browser forensics. Many apps out there are going to use like an embedded SQLite database to store things like chats and history and other little bits of information of configurations for an application. You're going to find that in mobile and a lot of web browsers as well. Now, we can also use some internal tools. You don't have to use third-party tools. You use things like the function DB log, and this is an undocumented built-in MS SQL function. Now, what's cool about this, it will let you look at active transaction log directly using things like standard SQL commands. Now, for the exam, SQLite forensics is heavily focused on the exam itself, particularly when we're talking about mobile forensics modules. So you need to understand that SQLite databases are going to consist of the .SQLite file and a WAL file, okay, a write-ahead log file, and an SHM, otherwise known as a shared memory file. Now, you need to get all three of these files to be able to complete an investigation. So know that those three files are going to be tied back to SQLite. Remember, as I said, you're going to need to know what files go to what type of database. All right, to summarize Chapter 10, when investigating the dark web, your primary focus should be on client-side artifacts like RAM, state files, and pre-cached data. Now, the reason for this is network traffic itself is going to be anonymized and encrypted. Now, when we're investigating database, on the other hand, remember that the transactional log, LDF, or bin log, depending if we're talking about MySQL, MariaDB, or MS SQL, is going to be our black box. Remember, it's our black box flight recorder that proves an attacker's intent. Finally, remember that deletion is rarely instant, and ghost records and slack space is going to hold the evidence that we may need to recover to get that stolen or destroyed data back. So the overarching thing of this chapter for the exam was that encryption and deletion are just hurdles. They're not dead ends. A skilled investigator will know where to find the residual artifacts that live on this host system. All right, so that's going to conclude the review for Chapter 10. If there's any questions, let me know. Otherwise, I'll see you for Chapter 11. So ensure that you have a solid grasp on these concepts before moving on, because database and dark web artifacts often are going to be intertwined and are going to be on the exam, okay? Especially in the scenarios. As an example, investigate a suspect who stole a database and sold it on a Tor marketplace. All right, I'll see you for Chapter 11.